We are continuing with the final exam review part 2, and this will cover a few questions from chapter 4 through 7. As you prepare for your finals, I encourage you to go back to all the previous study guides that we have used for this semester, for all the exams. Go through all your exams that we covered in this semester, your previous quizzes, worksheets, active homework, and your study guides. Okay, that should be the way you will be preparing for your finals. Here I'm only able to cover a few questions. I will not be able to cover every single topic from the 13 chapters, so this is just a few questions from chapter 4 through 7, right? So the first question is about how to represent a cycloalkane in a chair conformation, and then also to redraw that in a flipped conformation and circle the most stable conformation, right? So if you look here, this cyclohexane has an OH group that is on the axial position, and then we have the CH3 in equatorial position, chloride again in axial, another CH3 in equatorial, and this large isopropyl group in the axial position. So when we flip it, you can see that every axial position has changed to an equatorial, and every equatorial position has changed to an axial, right? So if you recall, when we flip it, make sure that you bring this carbon atom down and this carbon atom up. So that's how the flip is drawn for a chair conformation of cycloalkane. So when we do that, the OH, which was axial, now becomes equatorial. The methyl, which was equatorial, now becomes axial. The chloride, which was axial, now becomes equatorial. CH3, which was equatorial in the first conformer, becomes this was axial, CH3, which was axial in the first conformation, now becomes equatorial, and then the isopropyl group is now equatorial. All right, so the stability of a flipped conformer will be stable, will have the lowest energy if the larger groups are in an equatorial position. And here, one of the largest group is the isopropyl, so we will circle this as your more stable conformer because the isopropyl group is in an equatorial position. The next molecule is asking to take a planar structure of cycloalkane and redraw that as a chair conformer. And here we have only methyl groups. This methyl group here is pointing up. This methyl group is pointing down, and then this methyl group is again pointing up. So when you draw that, you have to make sure that you draw it exactly the way the planar structure is, except that now it is in a chair conformer, right? So it's good maybe to start numbering these. So you have 1, 2, 3, and 4. So at the 1, 3, 2, and 4 positions, we have the methyl groups. So if we take this as my 1 and this as my 2, 3, and 4, at the first position we have the methyl group pointing up, at the second position we have the methyl group pointing down, and at the fourth position we have again the methyl group pointing up. So in that way we get this as an axial, this also as an axial, and this one as the equatorial. The next question is about the IUPAC nomenclature of the given compound. Here again it's chapter 4. It's a multiple choice question, and you can see that they both are pointing to the same direction, same phase. This is down and this is down, so that means this should be a cis structure. So you can rule out C here because that's trans, and then that gives me the correct answer as B, which is cis 1,3 dimethyl cyclohexane. That should be 1,4. Okay, yeah, this choice should be cis 1,4 because it's 1, 2, 3, 4, 1,4 dimethyl cyclohexane. Okay, all right. Next question is about, this is from chapter 5, and we are looking at figuring out whether they are enantiomers identical or if they are diastereomers, or if they are mesocompounds. So for that, you will have to look at the chiral centers, if there are any, and then give the configurations, the absolute configuration as the chiral center. Okay. Now in this case, if you look, we have two chiral centers, which I'm highlighting with this color here, and the priorities are given, and as you look at the priorities, this chiral center is S and this is R, and if you have complete stereochemistry reversed at the chiral centers, then they are enantiomers. So the first pair is enantiomers. Second one, again, we have only one chiral center, even though this could have been mistakenly looked as a chiral center because a dashed bond is given. But remember that we need 4 different groups to be for something to be a chiral center at the carbon atom. So here we have 2 methyl groups here, so this cannot be a chiral center, right? So we only have one chiral center, which again I'm highlighting here, and you can see that it looks like that NH2 group has been flipped in these two, and so they should be enantiomers. Actually they are not, because see, they are not the chiral center. At the chiral center, the NH2 is not only flipped, but also we have drawn the mirror image of the molecule. So that makes these two molecules identical, right? So it is not enantiomers, but it is identical. Or if you're not sure, just do the priority again, and you can see that this is R, and this is also R, which means that if you have exactly the same absolute configuration at the two chiral centers, then they have to be identical. The last pair is again the same, that they both have exactly the same absolute configuration, so they should also be identical. Okay, remember that in here we do not have an example of diastereomers, but you do have to look at examples of how to identify diastereomers. So in diastereomers, the chirality at some centers will be reversed, while at other chiral centers it remains the same. Okay, so for example, if you had an RR as your original molecule, your diastereomer will look either RS or SR. Okay, so these are examples of how to identify different enantiomers, identical molecules, or if they are diastereomers. And for meso, remember that you should have a plane of symmetry as well as chiral centers. Okay, so one example would be like if you have 2 methyl groups here, and then you do have chiral centers, you have 2 chiral centers, but you also have a plane of symmetry. So this, if I had drawn another isomer of this with dashed bonds to the methyl groups, it looks like they might be enantiomers, but actually the plane of symmetry makes them a meso compound. Okay, so make sure you look at several examples of meso compounds, enantiomers, and diastereomers. Okay, all right. Next question is again back to identifying functional groups. So this is something you should always be able to identify functional groups in a given molecule. These are only a few, like we have an alcohol, a benzene, an ether, and alkene. However, I would again suggest that you go back to all the functional groups which we have studied in chapter 3 and review them one more time. Okay. Now in this case, the next question is asking you that what would be the starting alkene of this given molecule. This is from chapter 7, and you know that if you want to get a alkyl halide molecule, then a double bond or an alkene is what we would need, and here we see that either one of them would have worked. The next question is asking to draw a reaction coordinate diagram for a reaction with the following characteristic. It has to be a 2-step mechanism. It has to have an intermediate which has the highest energy. And first step is the rate determining step. Okay. And then delta G is positive. So keeping all this in mind, this would be a energy diagram. Let's redraw this one more time. Make sure that you label the axis energy versus reaction progress. Okay, and it has to be 2 steps, and also the intermediate has to be the highest energy. So that means if your reactants are here and we make it 2-step, and your products are here, and it has to be delta G positive, so your reactants and should be at a lower energy state and product should be a higher energy state. Okay, so here is your products, here is your reactant, here is your intermediate, and then the first step is the rate determining step, so this should have the highest energy of activation. Okay, so the energy of activation should be the highest for the first step. This is the second step into energy of activation, which is lower than the first. This is transition state 2, transition state 1. Okay, delta G is positive. Why? Because the products are at a higher energy state than the reactant. All right, this is from chapter 6 if you would like to review more about energy diagrams. Next one, draw a curved arrow to indicate mechanism. So this is chapter 6 where we learned about drawing arrows to show electron movement. Here it's a nucleophile and electrophile. So the nucleophilic carbon, which is the pair of electrons, is taking the proton from this alkyl halide here. So we have to, since the product is shown here, the arrow should be drawn from the negative charged species to proton. Okay, and then the bromine is coming out. So that is how the products are shown here, with the bromide having all 6 or 8 electrons around it, 4 pairs, and then we have the main organic product here. Next one is asking about explain carbocation rearrangement and hydride shift using an example. So carbocation rearrangement, remember that if there is a position that is available for the carbocation to shift, like going from a primary to a secondary or from a secondary to a tertiary, then hydride shifts can happen, and that is what is called as carbocation rearrangement. Okay, so the stability of carbocations is tertiary is more stable than secondary, which is more stable than primary, which is more stable than a methyl. Okay, so greater the number of alkyl groups or R groups on the carbocation, more stable it is. This is an example where you see that the first step is the formation of a carbocation. Now this is a secondary carbocation, but due to hydride shift, it can move to a more stable tertiary position, and that's how you get the product here, which is your alkyl halide. Okay. So going back here, this is chapter 7. If you would like to review carbocation rearrangements or understand more about carbocation, please make sure that you go back to chapter 7. Stability of carbocations is actually an important topic, so do some more practice problems on that. Here, this is from chapter 6. It's talking about a free radical mechanism where ethylbenzene is reacting with bromine in presence of light, where what happens is one of the hydrogens here at the benzylic position is replaced by the bromine, and so the product is given. You are asked to write the mechanism. Again, in the final, these are all multiple choice questions, but still the questions may involve mechanisms, so you may be asked to identify what can be an initiation step or a termination step or a propagation step, so you should be able to do that. Okay, so here the first step is initiation, where the bromine takes up light and forms 2 bromine radicals. In the next step, we drew half or fish hooked arrows, where the most stable free radical that will be formed is at this benzylic position. That's why the hydrogen at the benzylic positions are targeted. So you can see that the bromine removes one of the hydrogen atoms, and then it forms a radical here. Okay, the side product is HBr, and then we can have one more propagation step where this benzyl radical is reacting with another bromine molecule, and they again have arrows drawn to form the carbon-bromine bond, and a new bromine radical is formed. So how do you identify a propagation step? Is on your product side, you should get a radical formed, right? As long as a radical is formed on the product side, then it is called as a propagation step. Finally, we have the termination step where two free radicals combine to give you the final product, and there are no new radicals formed in the product site. So that is what is called as a termination. So we have initiation, propagation, and termination. Next question is again from chapter 7, a polar mechanism. Reaction is given with of an alkene with HBr. This is an electrophilic addition reaction. It's also asks you to identify the electrophile, nucleophile, and the intermediate. So in this case, our nucleophile is actually the double bond. Okay, it's the pi electrons on the double bond that are going to be nucleophilic, and your electrophile here is this hydrogen because bromine pulls off the electron due to more electronegativity of bromine. And remember, this is a polar reaction, so you will be drawing full arrows here, okay, unlike the free radical where you are doing half arrows. So the bromine removes the electrons from here, as a result of which this proton here has becomes electrophilic. Nucleophile attacks the electrophile, and you get the hydrogen, which is not shown, placed here, and then you get a carbocation at this more substituted carbon atom. Okay, and then the next step, Br comes and attacks the carbocation, and you get the final product. Okay, here you have to remember that you are following Markovnikov's rule, where we have two carbon atoms which form the double bond. This is your less substituted carbon atom, and the other one is the more substituted carbon atom. This is my more substituted. So according to Markovnikov's rule, the nucleophile goes and the carbocation is always formed at the more substituted. That is why we had the hydrogen go over to this less substituted carbon atom, and we got a positive charge at the more substituted. So then the Br attacks the more substituted, and then you get the product. So this is what is our Markovnikov's rule, which says that the carbocation will be formed at the more substituted carbon atom. So what is my intermediate? It said identify electrophile, nucleophile, and intermediate. We identified the nucleophile. Here is my electrophile, the hydrogen atom, and the intermediate is this, the carbocation, right? In my second step, the carbocation is my electrophile, the bromide is my nucleophile, and this is my final product. Okay, next question is on an IR spectroscopy, and I think this was one of our exam questions too in one of the previous exams. Anyway, be able to identify the major peaks for the functional groups. Here we see we have a ketone, we have an alcohol, we have an amine, and we have a terminal alkyne, right? So for a ketone, a peak around sharp peak around 1720 is characteristic of a carbonyl. So you can see that this one is our this peak here, that's my carbonyl peak, and so this should be my ketone peak, or this one, okay, A, compound A. The first one, this drawn here, is actually belongs to C, because you see that NH peaks, we had talked about vampire fangs, like identify, so that's my NH stretches, so that should be my C. This is my amine functional group. And that too, it's a primary amine, okay? A primary amine is the one which will have these two sharp peaks around this area here. Next one, for the OH, you can see this tongue-shaped structure, right? So that's my OH peak. And then for the alkyne, this characteristic peak here, that is my C triple bond C. It's a terminal alkyne, unsymmetrical alkyne, therefore you will see the stretch for a C triple bond C. Okay. You will be given an IR data, so sheets, so you don't have to memorize the values, but you will be asked to identify compounds using the NMR and the IR data. Okay. This is a set of multiple choice questions again, and it's asking you to classify this compound and also identify other functional groups. This one has a primary amine, so B is the correct answer, which has got a primary amine. It has got a primary alkyl chloride, and then it has a secondary alcohol. Next one is asking what will be the product. The product of this reaction is due to what is called as a hydride shift. This is again a case where your carbocation will be formed at a secondary carbon to begin with, but then there is a shift here because from a secondary you can actually move to a tertiary carbocation, and that's where the Br goes and attacks and you get the final product like this. So it is a result of 1,2 hydride shift. The third question is asking you about E and Z nomenclature. This is again chapter 7. All right, this is chapter 7 again. This is a functional group identification, which will be from chapter 3. All right. So here again, the main thing is you check at the 2 carbon atoms forming the double bond, what is the priority of the groups. So here we have the methyl group and an ethyl. So methyl becomes my low priority, this becomes my high priority. And on the other side, this is my high priority because you have a carbon atom connected to a, like I said, a double bond which has got higher priority than this carbon atom. So this is my low priority. So since the high priorities are on the opposite sides and low priorities on the opposite sides, this should be an E. And same thing here, we have when we look at the 2 carbon atoms forming the double bond, you can look at the priorities and that results in this also being an E. So your answer should be EE. Next question is asking which of the following compounds gives a carbonyl absorption as the highest frequency, right? So I think this was again one of our exam questions. So we had talked about this, that the one which will have the highest frequency will be the one that's least conjugated, okay? Because conjugation lowers the frequency. So here we see that the first one has a lot of conjugation, double, single, double, single, double. Here also this molecule is conjugated. You have a double bond, a single bond, and then a double bond. Here we have a double bond, a single, and a single, so the conjugation is broken over here, right? So that should be my correct answer. 3 is the correct answer. Next question, which of the following circled bonds gives a very weak or no stretching absorption in the infrared spectrum? So here the CC triple bond is the one that will give you no stretching because it's a symmetrical alkyne. Okay, symmetrical alkynes do not show C triple bond C stretches. Which radical is the most stable here? The one that has at the tertiary position, same thing like carbocation, that greater the number of R groups at the free radical, more stability there is, therefore this is number 2. Which of the following have R configuration? Okay, so again you check the priorities, and here in this example all 3 of them have R configurations because if you look at the priorities you can see that they will come out as R. Okay. Remember the rule that if your lowest priority is not at the back, then you swap it with the group that is at the back and then do your priority clockwise or anti-clockwise and then figure out whether it is R or S. Number 8 is asking you which of the molecules will have a plane of symmetry. In this here actually 1 and 3 both have a plane of symmetry, right? Why? Because you are not able to come, like you have one group here, another group here, but you have no 4 groups available, which means that there is a plane of symmetry in here. Same thing with 3 here, you are not having 4 different groups, so this one is also an example which has a plane of symmetry. The next question is about energy diagram, which is a 2-step process, one which has got 2 bumps on it. That's the 2-step reaction. The first one is just a 1-step. This one has 1, 2, 3 steps. This one is just a straight line, right? So your answer to this is B. Next question, identify what type of reaction is this. This is again chapter 6, where we studied the different kinds of reactions like elimination, addition, substitution, and rearrangement. In this case, by now you know after learning chapter 11 that whenever an alkyl halide is treated with a strong base, elimination reaction happens. So that's how you end up forming a double bond, right? So this is an example of an elimination reaction. Next one is asking what is the correct IUPAC name of the following alkene. You have to number it in such a way that you give the lowest priority to the double bond, right? So you will go from here 1, 2, 3. At first position you have an ethyl group, so 1 ethyl, 3 methyl, cyclopentene, and that is B is your correct answer. The next question is asking how many stereogenic or chiral centers are there in the molecule. So you can see that we have 2 chiral centers. Your double bonds carbon atoms cannot be at chiral center, so the only chiral center that you have here is these 2. Okay, so that's why the answer is 2. Next question is identify the again absolute configuration, but this is what is called as the Fisher projections. Okay, so if you are looking at chapter 5, that's where you will find this. In Fisher projections, remember that if your lowest priority is on the horizontal bond, like in this case, then you do the assign priorities, and then you do your clock. Is it clockwise or anti-clockwise? But if the lowest priority is on the horizontal bond, you swap your answer. So this comes out to be S, and similarly this other chiral center is also S. Okay. Here again, see, this is my lowest priority, right? So that's also on a horizontal bond. So whatever your direction you get, if it is clockwise or anti-clockwise, you do that and then you swap your answer. Which of the following could act as an electrophile? Remember, electrophiles are positively charged species. So here H3O plus is what would behave as a electrophile. Degree of unsaturation. All right. So remember the rules that halogens, when you have halogens in your molecule, you add one hydrogen to it. If you have nitrogen, you subtract one hydrogen from it, and then for oxygen you ignore it. Okay, so in this case, if you add one hydrogen, it will be C11H13, but then you're subtracting one nitrogen, which becomes C11H12. So that's your hydrocarbon that you will compare it to the saturated analog, and then when you figure out the degree of unsaturation, this will be 6. This is again something that you should look for in chapter 7, degree of unsaturation. What is the IUPAC name of the following compound? So this is an alkene. Again, make sure that you know how to designate an E or Z nomenclature. Answer comes out to be C. What type of carbocation is shown here? So this is a tertiary carbocation. It's asking what type of reaction does this show here. So it's a termination step in a free radical reaction, because when 2 radicals combine, it becomes a termination step. What type of reaction is shown here? Another elimination reaction. Okay, so we have removed an OH group or a water molecule here, and we have made into an elimination reaction. Stability. Oh, sorry. If here we are asking if you have a formula C3H4, which of the following is an incorrect statement? So if you have C3H4, your degree of unsaturation, that's the first thing you should do. You calculate the degree of unsaturation. It comes out to be 2. So if it is 2, then it can have 2 double bonds. That's a correct statement. It can have 1 ring and 1 double bond. That's also a correct statement. It can have 1 triple bond. That's also a correct statement. And it can have 1 double and 1 triple. That's the incorrect statement, right? Because with degree of unsaturation 2, you cannot have 1 double and 1 triple, because that will make it to degree of unsaturation equal to 3. Okay. Then which of the following compounds contains 3 degrees of unsaturation? So this one has 4 degrees. This one has 1, 2, 3, 4 degrees again. This one has 1 degree. So this is the one that has got 3 degrees of unsaturation. 2 double bonds and then the ring. Which of the alkenes is most substituted? Or in other ways, you can also look at the stability, right? So greater the substitution, okay, more substituted alkenes are more stable. Okay, remember that. The more the substituted alkenes is more stable. So in this example, it's only asking you which is the more substituted. So this is my most substituted, because see, we have 1 R group, a 2nd R group, a 3rd R group, and a 4th R group, right? Here, this one has, so it says a tetra substituted alkene. This is only 2 R groups, so it is a di substituted. Here again, we have only 2 R groups. This is also a di. And this one also has only 2 R groups, so that's also a di. So the one which has got most substitution is the tetra, and that will also be the more stable alkene. So this is a quick, a few questions from chapter 4 through 7, but make sure you go back to the exams and the study guides for all these units, and also do some practice problems from active to help you prepare for your final. We will do one more part 3 for the final exam review, which will include the other chapters from 8 through 11. 8 through 11, and then also we'll have a couple of questions on NMR, which is 13.